Okay, so we are going to start chapter 9. Some of us, I don't know, 7 of us maybe, were in class on Tuesday, but for the rest of us, we got to cover this material. So when we come back after the break, we're going to be ready to go. So we're going to start talking about bonds, right? And when we start talking about bonds, we start building compounds. So in chapter 3, we learned how to name compounds, but we didn't know how to draw them. Or how to build them ourselves. So we're going to take all the stuff we learned about naming in chapter 3, and we're going to now learn how to draw them all. So if you recall from chapter 3, of which there are several videos up in case you need a reminder, those are all up on Blackboard, there are 2 families of compounds that can be formed. Largely, there are others, but the 2 largest families of compounds on Earth are ionic and covalent. So it's important that we're able to come up with definitions of what ionic and covalent means. And so there are a couple different things that you have to know about each one of these. Ionic things happen when metals bond with nonmetals, right? So we have to have metals bonding with nonmetals. And we learned in chapter 3 how to name those. And there are all kinds of rules about that. So I've left up here for us a small periodic table because you have to be able to figure out who your metals are and who your nonmetals are. So the metals are everything here in maroon, and the nonmetals are in yellow. So when something from this part of the periodic table bonds with a nonmetal, we have an ionic compound. We're not going to spend a lot of time drawing ionic compounds, but I have one example up for us tonight. We're going to spend most of the rest of the semester talking about covalent things. So covalent things are when nonmetals bond with other nonmetals. Right? So when these 2 yellow compounds come together from this side of the periodic table, that would give us a covalent compound. Okay, when ionic things form, right, when a metal comes together with a nonmetal, metals always lose electrons, where nonmetals always gain electrons. And so we have an example that we'll look at a little bit later. But it is a complete transfer of electrons. So that guy gives up his electron, it goes over to the nonmetal, it doesn't come back, it's a complete transfer. So if we look at what happens when sodium does that, if sodium gives up an electron, he develops a positive charge. And if he runs into a chlorine who accepts that electron, he builds up a negative charge. And then these charges hold each other, or hold the sodium and the chloride together, circles. They hold those guys together, the negative and the positive charge. That's an attraction, but it's not exactly a bond. So these guys are held together by electrostatic attraction. But it's not really a bond. So when a water comes floating by, right, we know that what I've drawn here, NaCl, is just table salt. When a water comes floating by, we know that water dissolves salt. And it dissolves salt because there are a lot of electrons over here on oxygen, and sodium's feeling positive, right? And so the water can come over and pull these guys apart. So he'll pull the sodium over towards him, and this electrostatic attraction will be overcome. And so salt dissociates, right? This table salt, sodium chloride, dissociates in water. So these guys, ionic guys, I think of them as dating, right? If they were, if we were to gauge their relationship, I'd say they're in the dating phase. And so that's how I characterize an ionic electrostatic attraction. Covalent is a very different kind of bond. So when a nonmetal bonds with a nonmetal, neither gives nor takes the electron, they share. So this is a complete transfer of an electron over here, and this is the sharing of electrons between nuclei of nonmetals. Because they both nuclei, let's say it's just a carbon being bonded to another carbon, because they both depend on this electron that's zooming back and forth, this is what we call a chemical bond. right? I do not have a chemical bond in ionic things. I do have a chemical bond in covalent things because they are sharing this electron. So it's important that you know what kind of elements make up a covalent bond, but also what a covalent bond is by definition. Likewise, you have to know that sort of stuff about ionic things too. You have to be able to fully differentiate between an ionic and a covalent bond. So we know now that a covalent bond is expected between two nonmetals, and it is a sharing of electrons between nuclei. So we're going to now go through and figure out how they share electrons and how they know how many electrons to share. Okay, so when two, like in my example, I just do that carbon with a carbon and a little bond between them. When two elements come together, when two atoms come together, they are only willing to offer up their outermost electrons, right? So all atoms have internal core electrons and external valence electrons. We've used this word valence before. So if we look at something like lithium, right? Lithium has an electron configuration of 1s2, 2s1. If we were to follow along on the periodic table, that's what we would get. So as I drew that out here for you, we see that the 1s subshell is filled and the 2s subshell has one electron in it. So if I were to ask how many valence electrons lithium had, I would go to his outermost energy shell. So the 1 is a core shell. Those are internal, right? But the 2, that is the outermost shell. So that is his valence shell. So in his valence shell, everything with 2's, in his valence shell, he has 1 electron. That means when lithium comes into some bonding situation, lithium is only willing to bond with 1 electron. Right? He is not willing to bond with his core electrons. Those are his. He's only willing to share or give up his valence electrons. So we're going to have to get good at counting up how many valence electrons live in each atom. Okay, so that's lithium. He has 1 valence electron. If I were to look at beryllium, I could figure out his electron configuration, or I could look at his orbital box diagram, and I could see that beryllium, again, these are core, right? And these are your valence. So beryllium has 2 valence electrons. 2 valences. And as we head across the second period, right, I'm just moving across the second period of the periodic table here, I could look at boron, and now I know that boron has 2 subshells in his second energy level. So now he has access to his p shell. So if I were, again, these are core, these are inside. He's not willing to bond with those, but boron is willing to bond with his valence electrons. And so he's got 3 valence electrons. So we could do this for every element, right? We could draw out these we could draw out the electron configurations and the orbital box diagrams for each of the elements in the periodic table, and we could look for the outermost shell, and then we could add up the electrons in the outermost shell, or we could look at the picture and we could see that carbon has 4 valence electrons, nitrogen has 5 valence electrons, right? But it turns out that there's also an easier way to go about it. Oops. That's the next slide. Just kidding. I'll show you the shortcut later. So if we wanted to, I'll show you the easier way to find these. You don't have to write out the electron configuration every time. But if I wanted to come up, all of these ways of showing you how many valence electrons there are, they take a lot of work, right? They take a long time. You have to write the full electron configuration. That's annoying. You got to draw all these boxes. That might be annoying. And so Lewis dot structures, right? If I were to just show you what this is the title of chapter 9, I think. Lewis dot structures are just that. This guy Lewis came up with this very simple way of showing elements with their dots, right? So spoiler alert, there it is. So we set up here that lithium had 1 valence electron, right? I could see it right here. I could see it in his orbital box diagram. But Lewis just said, what if we just put the symbol and then we put 1 dot on it? And that 1 dot would tell us that lithium is willing to bond with 1 external valence electron. So these are Lewis dot structures moving across period 2 and period 3 on your periodic table. So you can start to see a pattern, right? Everybody in group 1, everybody in the alkali metals, lithium, sodium, potassium, rubidium, they all have this one dot. So they have one valence electrons. So the group numbers across the top of the periodic table are also the valence electrons. They are the same. So if I wanted to just go look at oxygen or any element underneath oxygen and I wanted to know how many valence electrons it had, I would see it's in the 6th group, and I would know that it would have 6 valence electrons. Now your periodic table doesn't have the group numbers, I think, but you can also just count, right? You just start on the left and you count 1, 2, 3, 4, 5, and so on, and you'll get all the way over here to 8, right? So that's the easy way to think about how to count valence electrons, but also how to draw these Lewis dot structures. Okay, so let's, for example, look at bromine. So if we wanted to write the entire electron configuration for bromine, I would start with argon as an abbreviation, and I would say he's got 4s2, 3d10, 4p5. So if I wanted to go through and identify bromine's outermost shell, I would have to see that the 4th shell is the outermost shell. Now, lots of us got this wrong on antimony on the exam. So when you get your exams back, take a look to see if you fell into this category. When we're looking for valence electrons, we are looking in the outermost energy shell, which is 4. This shell is the 3rd shell. The 3rd shell is not the outermost shell, right? Because 3 is smaller than 4. That's the only thing we're doing here. 3 is smaller, so he's not the outermost. Everybody in the 4th energy shell has valence electrons. So the S subshell has 2 valence electrons, and we will add those together with the P subshell electrons, that's 5. And so bromine has 7 valence electrons. But if I go back and look, bromine falls under chlorine, right? So bromine would be here if we were to draw period 4, and everybody in the 7th group has 7 valence electrons. So just knowing that bromine lives under chlorine tells me it's 7, but if I wanted to draw it out this way, I could see that it's 7 valence electrons. So if I were going to draw his Lewis dot structure, I would draw it so it looked just like fluorine and just like chlorine, right? I'd draw it with 7 dots to reflect the 7 electrons. Okay, so this is the picture where I'm just showing you that as long as you can count from the S's, right, through the S subshell, skip the D's, we don't need those, because these are always one shell behind, and then count the P's. If you can count from left to right, S plus P's, then you will know your element's valence electrons. So if I wanted to find out arsenic's, right, I could just know that he's in the 5th group, or I could start over here and I could count 1, 2, skip, 3, 4, 5. So he's got 5 valence electrons, so arsenic would have 5 valence. This is going to be an important skill when we start drawing these Lewis dot structures, right? So if I looked at this example, where bromine, which we already determined has 7 valence, bumps into another bromine, this guy's going to bring 7 electrons to the party, this guy's going to bring 7 electrons to the party, and when they collide, they're going to share electrons, right? They're going to share because they're covalent. And so we're going to learn how to draw shapes similar to this so that we can understand how a bromine and a bromine would bond together, or how they would share electrons. This is ionic, right? This is sodium bonding with oxygen. They don't share, right? This is sodium giving up his electron. He's just giving it away. He lets it go entirely and it goes over to oxygen. This sodium does the same thing, gives it up, it goes over to oxygen. And so when we look at something that's ionic compared to something that's covalent, we see that this has a bond, right? That is a bond come about by sharing of electrons. This has no bond. This only has electrostatic attraction. That controls a lot of how these things behave physically in the world, so I'm mentioning it again and again. Electrostatic attraction. So again, we're not going to do much of this. We're not going to show a lot of these ionic Lewis dot structures. We're going to learn how to use Lewis dot structures to build these covalent compounds and show how sharing occurs. In order to do this, we have to have a really strong understanding of what valence electrons are, and so we understand how many electrons are available for bonding, because only valence electrons bond. Only valence electrons are available for bonding. Okay, in the next video, I'll go on and on about some examples, and I'll show you how to count up valence electrons and how to draw these Lewis dot structures. When you come into class on Tuesday, you got to know how to draw a wide range of Lewis dot structures. If you don't, you'll be incredibly behind, and I won't necessarily have time to help you get caught up. So please watch this video, read the first few sections of Chapter 9, and watch the next video that's coming up about how we can practice these things.